I'm so bad at these.
These conversions? Okay.
Yeah.
Well, as you do the conversions, there are a few different ways to do it. What I think is the easiest way is to do that conversion factor with the fractions. So 8 rods, we're going to make it 8 rods over 1. And now, I don't really want equal sign there. We're going to use a conversion factor. And in our conversion factor, we're going to use our rules of fractions. And one of the rules of fractions that we can cross cancel. So since I have rods here, and I'm getting rid of rods, I'm going to put rods here so that they'll cancel out. Get that down below that so it's out of the way. So then I have rods and yards in the problem, so that means yards have to go on top of that conversion factor. Then I look up my relationship, and I see that 1 rod equals 5.5 or 5.5 yards. So there's my relationship. And now the rods do cancel out. 8 times 5.5 yards is 44 yards. On bottom, 1 times 1 is 1, so that's just 44 yards. Okay, good. Over here then, 48 ounces, we're going to do the same thing. 48 ounces over 1. And we're going to multiply by a conversion factor. Again, we have ounces here that we're trying to get rid of, so we're going to put ounces on bottom. We're converting to pounds, so pounds are going to go on top. We look up our relationship. 1 pound is 16 ounces. So the ounces cancel out. We have 48 times 1 pound is 48 pounds. We have 1 times 16 is 16. 48 pounds divided by 16 is 3 pounds. So 48 ounces is 3 pounds. Not so bad. So then here, 2 gallons. This one's a little bit tougher. We got 2 gallons, we put it over 1. We are getting rid of gallons, so we're going to put gallons on bottom. But we look up, we don't have a direct relationship from gallons to pints. We have gallons to quarts. 1 gallon is 4 quarts. That'll cancel out the gallons, but right now what we have left is quarts. So we have to get rid of quarts. So quarts are on top here, so to get rid of it, I'm going to put quarts on bottom. And I do have a relationship between quarts and pints. 1 quart is 2 pints. So now the quarts cancel out. So on top I have 2 times 4 is 8, times 2 pints is 16 pints. On bottom, 1 times 1 times 1 is just 1, so 16 pints over 1 is just 16 pints. For my metric conversions, I can do the same type of thing with a conversion factor, but it's much easier if we keep the metric chart handy and just refer to it. Remember, in a metric measurement, our main unit is in the center, whether it's a meter, a gram, or a liter. And I'm just going to use grams as my abbreviation. This would be deci, so DG would be decigram, decimeter, deciliter. Centi is a hundredth. Then it's milli. Centigram is a thousandth, yes. Going the other way, it's deca, which is D-A-M, D-A-G, D-A-L. Then hecto, which almost never gets used, and kilo. Now we had mentioned the one that gets used the most, obviously, is our main unit. We tend to use the thousandth and the 1,000ths. The other ones only get used in special applications. Like for centimeters, the centimeter gets used a lot in the U.S., only because it's the closest thing to an inch, and the inch is so ingrained in our culture that we latched onto the centimeter. But in most European countries, millimeter is actually more common than centimeter. Deciliters gets used in medical terms. If you do a blood test, like let's say you go and have your cholesterol checked and it comes back as a 180, That's 180 milligrams of cholesterol per deciliter of blood is what that's coming out to be. So anyway, we can use this chart to do our metric conversions. From centimeters to meters. Here's centi, here's meters. To get from centimeters to meters, it's 2 spots to the left. Our decimal point has to go 2 spots to the left. So 0.072. .93 liters going to milliliters. Liters would be right here. 1, 2, 3 spots to the right to get to milliliters. So here's my decimal point. I have to go 1, 2, 3, add a 0. That's 930 milliliters. Finally, kilograms to grams. Here's kilo. Here's grams. So we're going to go 1, 2, 3 spots to the right to get from kilograms to grams. So my decimal point goes 1, 2, 3 spots to the right. That would be 70 grams. What do you think? Nope. Those metrics don't work?
I was moving the decimal place in the wrong spot.
Okay.
Look, I understand, but I don't understand how it works. I mean,
Yeah. You can make it work, you just don't know why it works?
yeah.
Okay.
And then it drives me nuts.
Well, the reason it works is in the metric system, everything is multiplying or dividing by 10. Everything's 1/10 or 10 times. And because of that, when you multiply or divide by 10, it just moves the decimal point 1 spot. So in the other way you could have looked at that is, you go from centimeters to meters. We're going 1 spot to the left is dividing by 10. Another spot to the left is dividing by 10 again. So you got your 7.2 centimeters over 1. Put a centimeter on bottom. 1 centimeter, actually 10 centimeters is 1 decimeter. That's getting from centimeters to deci right there. And then you could do, takes 10 decimeters to equal 1 meter. So now you're going from the deci to the meters there. So the centimeters cancel out, the decimeters cancel out. You're going to be left with meters. 7.2 times 1 is just 7.2 meters. 1 times 10 times 10 is 100. So 7.2 divided by 100 is 0.072.
I think I was confused because when you draw it out like that,
Sure. Just move it, yep. But yeah, it's just a way of shortening it up, is every spot on the chart is dividing by 10 or multiplying by 10. So by using the chart, it is just a shortcut. Now down here, 7 and 8, I put kind of at the bottom because I didn't expect you to necessarily be able to do those yet. But I put them on there just to see how you can handle it. These we need to get the conversions out of the book. Making sure I have the right ones here.
You don't really want me to open my book.
Yeah, you actually get to open your book.
wow.
It's in pristine condition. It's mint, man.
I might hurt the value.
Find out twice. Just once to look at it and once try to figure out where we were at.
That's what I'm trying to find, is what page. This is a new edition, so I have to figure out new page number.
Yeah. Opening this on my stove.
Yeah, you broke her open, huh? Looks like it's page 576. First time you open the book and we're almost at the end of it.
Right?
So on page 576 there are conversions between metric and standard, US. In fact, this book doesn't even call it standard measurement anymore because metric measurement has become the world standard.
Except for us.
So they call it US measurement and metric measurement. So we need to convert, here we got 72 inches. I'm going to set that up as 72 inches over 1. In our conversion factor, we need to put inches on bottom and meters on top. Inches have to go on bottom because that's what we're getting rid of. So the inches are going to cancel out. We look over here in our US length. We've got 1 inch is 2.54 centimeters. And we've got 1 meter is 3.28 feet. Or 1 centimeter is 0.0394 inches. So either way, they do not have a direct conversion from inches to meters. So we're going to have to scrap this, and we're going to have to do an intermediate conversion. So we still have to have inches on bottom here. We either have to go to feet, so that we can get from feet to meters, or we have to go to centimeters and then convert centimeters to meters. Either way. Which did you guys do? Feet first or? Feet first. And 1 foot is 12 inches. So now the inches cancel out. 72 times 1 foot is 72 feet. 1 times 12 is 12, so that's 6 feet. Many of you probably just noticed 72 inches is 6 feet. Now from that, the 6 feet has to be converted. I'm going to put feet on bottom, and now hopefully I have a conversion straight to meters. And I actually have two. I have 1 foot equals 0.305 meters, and I have 1 meter equals 3.28 feet. How do I know which one to use? Well, in reality, either one of them will work. Unfortunately, they round slightly different, and my math lab can't handle that. So what my math lab wants is it wants you to use whatever one puts a 1 in the denominator, so that we're dividing by 1 and not dividing by some other number. So 1 foot, that looks like we're going to be using the 1 foot equals 0.305 meters. So the foot cancels out. We've got 6 times 0.305, which is 1.83 meters. You got it. Had we used the other one, so if we had 6 feet over 1, had we used the one that was 1 meter equals 3.28 feet, 6 times 1 meter is 6 meters. 1 times 3.28 is 3.28. 6 divided by 3.28 is 1.83. So in this case, it rounds exactly the same. This was exactly 1.83. This one was 1.329268. So there's a slight difference. If we're rounding the nearest hundredth, those both came out the same. If we were rounding to the thousandth, they might have been slightly different. So my math lab is always looking for the one that puts a 1 in the bottom of this, the denominator of this conversion factor. You were getting it right, but it was telling you it was wrong because it was just outside the round off.
Well, yeah, they actually have a little thing in there where they have to chart bigger.
Yep.
It's like, oh, okay.
So now I have 18 gallons going into liters. What's going to go on bottom in my conversion factor? Gallons or liters? Gallons, because I got to cross cancel the gallons, right? So liters have to go on top. And I want 1 with the gallons. So I look, I have 1 gallon is 3.79 liters. That's a rounded conversion factor. The one that I typically have used is 1 gallon is 3.785 liters, but that's close enough. They're keeping all their conversion factors to two or 3 decimal places. So the gallons do cancel out. I have 18 times 3.79 liters is 68.22 liters. On bottom, 1 times 1 is 1, so it's just 68.22. Okay, so there we've got Ashland up and running. We've just been reviewing some of our conversions. Is my computer screen showing okay at both sites there?
Yeah, we can see it in Ashland.
Okay, just wanted to make sure everything was working right since we had some difficulties this morning, it looked like. Okay, so that is our conversions between US and standard. And again, that is page 576 in the book that has that page full of conversions. My math lab usually does give it in the problem. If you can click on the little button to pull up the conversion chart, or it'll say right in the problem what the conversion is, but that one is there. So as long as we know how to do this conversion factor thing, the metric to standard or metric to US and US to metric is not anything different than what we've done. What might be different than what we've done, I shouldn't say what will be different than what we have done, is dealing with area and volume conversions. We mentioned this briefly. Let's say that I have an object here that is 4 square feet. And I want to know how many square inches that is. First of all, do I have to turn that 4 into a 16? Now you might be looking at me wondering, why would he ask that? Well, because I have students who do this all the time. They see the squared there, and they think they've got to square the number. That squared is part of the unit. It is not really a power that's asking us to do anything. It's part of the unit that's telling us that this is not a linear foot. It's not a foot that's in a straight line like that. It is a square foot. So it is a square that is 1 foot by 1 foot. And we mentioned this briefly last week. That means it is 12 inches by 12 inches. So the area, 12 times 12, is 144 square inches in 1 square foot. So when we go to convert this, we have 4 square feet. We're going to put square feet on bottom to cancel them out. Square inches on top. 1 square foot is 144 square inches. Square feet cancels out. 4 times 144 is 576 inches squared. 1 times 1 is 1. So that is just 576. So what if I have something that is 54 square feet and I want to go to square yards? Well, it's 54 square feet over 1. Square feet are going to go on bottom and square yards on top. But what is our relationship between square feet and square yards? Well, if this were linear yards, if this is 1 yard, how many feet are in 1 yard? That's 3 feet. So a square yard, being 1 yard by 1 yard, is 3 feet by 3 feet, which is 9 square feet in 1 square yard. So over here, 1 square yard is 9 square feet. The square feet cancel out. 54 times 1 square yard is 54 square yards. 1 times 9 is 9. And we do have to divide out. 54 square yards divided by 9 is 6 square yards. You'll notice the squared on the feet and the yards had no effect on the numbers. What it did change was the conversion factor because it changes the units. The units are not feet and yards anymore. They're square feet and square yards. Or we might have 2 cubic feet going into cubic inches. So the cubic feet have to be on bottom so they cancel out. Cubic inches on top. Now we know the feet are larger units. That's going to be our 1. But how many cubic inches are in a cubic foot? There you go. It's 1 foot by 1 foot by 1 foot, which is 12 inches times 12 inches times 12 inches, or 1,728 inches cubed in 1 cubic foot. So this is going to be 1,728 up here. The cubic feet cancel out. 2 times 1728 is 3456 inches cubed. And on bottom, it's just 1 times 1, so it's 1. So 3,456. What you should be noticing here is where this power does come into play, as we've mentioned, is in our conversion factor. And what it does is it actually does cube or square or whatever the power is, our conversion factor. 1 foot equals 12 inches. Well, 1 square foot equals 12 squared, or 144 square inches. Think of it like this. If I square both sides of the equation, which is legal, I can do that. Remember when we were doing this with algebraic numbers, you squared the number. What's 1 squared? 1. Then you squared the variable. X squared would become x squared. Well, feet squared becomes foot squared, or square feet. Over here, we got to square the number. 12 squared is 144. Then inches squared becomes square inches, or inches squared. And then, of course, for cubic feet, it was 12 cubed, or 1,728 inches cubed. So if I have 324 cubic feet, in your notes, try to figure out how many cubic yards that's going to be. Okay, so which one is larger, a yard or a foot?
A yard.
A yard. So that's going to be the 1, right? How many feet are in a yard? 3. But this is cubed. So what is 3 cubed? 3 cubed.
3 times 3.
Yeah, which is 3 times 3 is 9 times 3 is 27. There we go. So the feet cubed cancels out. 324 times 1 cubic yard is 324 cubic yards over 27. So divided by 27, that is what? 12. Thank you. 12 cubic yards. Not so bad? Okay. When we get into the metric system, of course, we're going to be talking about just meters. We're going to forget about grams and kilograms for a while here. When we converted 280 centimeters into meters, now we said we're moving 2 spots to the left on the chart. So the decimal point had to go 2 spots to the left. It's 2.8 meters, right? And the reason that worked was there were 10 centimeters in a decimeter, so we had to divide by 10 to go back. 10 decimeters in a meter, so we had to divide by 10 to go back. What if, however, (280 centimeters squared going into meters squared? Well, now there are not 10 square centimeters in 1 square decimeter. There's 10 centimeters in 1 decimeter. But a square decimeter is 10 by 10, or 100 centimeters squared. So now each spot on the chart is multiplying or dividing by 100. So each spot on the chart is moving the decimal point 2 spots. 100 moves the decimal point 2 spots. So if it's squared in our units, each spot on the chart is multiplying or dividing by 10 squared, or 100. So it's moving it 2 spots. So centimeters to meters is still 2 spots to the left, but each spot is 2 decimal places. So the decimal point has to move 4 spots. 1, 2, 3, 4. We got to add a 0 there. So that is 0.028 meters squared. Well, if it were cubed, yeah, that would be 10 by 10 by 10, which is 1,000. There'd be 1,000 cubic centimeters in 1 cubic decimeter. And that goes for any place on the chart. So now if it's cubic, every place on the chart is multiplying or dividing by 1,000, which moves the decimal point 3 places. So to get from centimeters cubed to meters cubed, still 2 spots on the chart, but each spot is 3 decimal places. So we're going 6. So we go 1, 2, 3. We have to add zeros, 4, 5, 6. So that is 0.00028. Now I get the question all the time. Do I need to have that 0 here at the end of that? That's a very good question. A little bit deeper conversation than I want to have about measurement in this class. But we did bring it up a little bit last week, I believe. That 0 there is telling us something about the measurement. That 0 is telling us that, well, here it would be telling us something about the measurement. Up here it doesn't necessarily tell us much. But that 0, it's something called significant digits, asking us, is that part of the measurement? When we see 280 centimeters, the way that's written, that either implies that when we measured it, we had a ruler that could measure to the nearest centimeter, and it happened to be closest to 280. Or, So it's literally between 279.5 and 280.5 centimeters. Or it could imply that we had a ruler that measured to the nearest 10 centimeters and it was closer to 280. So that would be anywhere from 275 to 285. The way that's written, we don't know what that is. So we would have to assume the worst, that it was 275 to 285, that it was a bigger error. This class, we don't talk about measuring devices and the built-in errors and measurements. Anybody who's in a technical field like machining or construction or automotive, we would spend that time to talk about, when you see that measurement, what does that imply as far as the error in the measurement? For this class, we're not really worried about it. But I wanted to bring that up. I will not mark it wrong in this class if you don't put that 0 in there. I think my math lab won't mark it wrong either if it's not there. But there are cases where that 0 does need to be there because it tells us something about the measurement. So let's have you guys do some examples here, see what you guys can do with the area and volume. So let's take 0.037 centimeters squared converted into millimeters squared. Let's take 39 millimeters cubed into centimeters cubed. 0.28 meters squared into millimeters squared. Try those three in your notes and we'll talk about them here in just a second. Okay, so for the first one, centimeters to millimeters is one spot to the right on the chart. But this is squared, so that means each spot is how many decimal places? 2. So the decimal point has to go 2 spots. So that becomes 3.7. So I'm going to stop there. How many of you had that right? Show of hands. Any questions on how I did it? Because it's squared, every spot on the chart has to be 2 decimal places. So it went 1 spot on the chart, the decimal point had to go 2 spots. Millimeters to centimeters is going the other way. It's 1 spot to the left, but it's cubed. So each spot on the chart is 3 decimal places. So instead of going 1 spot to the left, I have to go 3 spots to the left. 1, 2, and I have to add a 0 to get my third one. So that's 0.039 centimeters cubed. How many of you had that one right? That one you got good. Any questions on that? Again, it's 1 spot on the chart, but because it's cubed, each spot on the chart moves the decimal point 3 decimal places. So down here, 0.28 meters squared to millimeters squared. Again, we start out by looking at meters to millimeters, which is 3 spots to the right on the chart. But since it's squared, each spot on the chart is 2 decimal places. So 3 times 2 is 6. So that decimal point has to go 6 spots to the right. So 1, 2, then we have to add zeros. 3, 4, 5, 6. So that is 280,000 millimeters squared. That's one that we'll have to be careful of and just keep working on as it comes up. The next one combines these conversions into bigger problems. For example, if I told you guys that I could throw a baseball 90 feet per second, would you believe me? 90 feet per second. Now, 90 feet is the distance from first base to home plate. So I'd be saying I could throw the ball from first base and it'd be at home plate in 1 second. Is that fast?
Yeah.
Well, what are we used to seeing speed expressed as?
Miles per hour.
Miles per hour. Very good. Now remember when we talked about rates a week or so ago, proportions and rates, actually about 2 weeks ago now, 90 feet per second is really 90 feet per 1 second. We want that to become miles per hour. So I'm going to change the feet and the miles. Now I'm going to change the feet first. I'll put feet on bottom, so I'm going to go to miles. The feet cancel out. 1 mile is 5,280 feet. What units do I have right now? Well, the feet cancel out. That'd be miles per second. I have miles on top, seconds on bottom. Want to get rid of the seconds. Now here, where do I have to put the seconds in my conversion factor to make them cancel out? Yeah, because they started out on bottom, I have to put seconds on top. Now I don't really have a direct conversion from seconds into hours. So I'm going to go from seconds to minutes. 1 minute is 60 seconds. So that takes the seconds out. But I still have to go one more step to get from minutes to hours. 1 hour is 60 minutes. So the minutes are gone. Now I have miles on top and hours on bottom. That's what I want, miles per hour. So on top up here, I'm going to do 90 times 1 mile is 90 miles. Times 60 is 5,400. Make my tongue work here. Times another 60 is 324,000 miles. On bottom, we've got 1 times 5,280 times 1 times 1 hour. That's 5,280 hours. Divide that out, we get 61.3, I believe. .36 miles per hour. I could probably still throw that. I'd have to warm up for a while, and I could probably only throw that fast 4 or 5 times before I'd have to rest. Yeah. But I could probably still throw that fast. So you can see there, the way we use those conversion factors helps us work with these compound units like this. We have pumps. We're used to pumps being rated as what's called CFM. CFM is cubic feet per minute. So let's say we need to have a pump that is rated at least 9 CFM. That's what we need. We have a pump that says it can pump 2,000 gallons per hour. Will that work? Will that be fast enough? Is that at least 9 CFM? Well, let's take that 2,000 gallons over 1 hour and convert it. Let's do the gallons to cubic feet first. 1 cubic foot is, we're going to go 7.5 gallons is what it comes out to be. It's like 7.48. So the gallons cancel out. We're in cubic feet per hour. What else do we have to get rid of? Hours are going to go to minutes. 1 hour is 60 minutes. So we have 2,000 times 1 cubic foot. That's 2,000 cubic feet. 1 times 7.5 times 60 is 590 minutes, right? 2,000 divided by 590 is going to be way short. 3.39 cubic feet per minute. Yeah, so it's not nearly big enough. That would require close to, it'd be of a 5,500 gallon per hour pump to get that. Actually, 5,500 might be a little short. 6,000 is right around 10 cubic feet per minute. Other things you might have something that is rated at, let's see here. Let's say it is 12 ounces per square inch. We need to know how many pounds per square foot. So it's 12 ounces per 1 square inch. Let's get rid of the ounces first. Where are the ounces going to go? Bottom. What goes above them then? We're going into pounds. 1 pound is 16 ounces. So the ounces are gone. What do we have to do next? So where do we put the square inches? On top. Square inches and then square feet on bottom. What's our relationship there?
144.
Perfect. 1 square foot is 144 square inches. So you're at 144 over 1. So the square inches cancel out. 12 times 1 pound times 144 is 1,728 pounds. On bottom, 1 times 16 times 1 square foot is 16 square feet, which comes up to be 1.09, I believe. Sorry, 10.9 or something like that. I mean, $108, sorry. 108 pounds per square foot. What do you think?
Isn't there a simpler way?
There are.
There's got to be a simpler way.
If you have charts, there are charts out there that have direct, like that page 576 in our book. There are charts that have those direct conversions, but there are so many different combinations of these units.
Right.
That you'd be looking through those charts. I mean, those charts are only 4 or 5 pages long. You'd be pouring through looking for the right unit.
There's got to be an app.
There are phone apps. There are cell phone apps that do it. But I will warn you, some of them, there are certain units that... Remember, we talked about how... how the yard is not consistent. The U.S. yard is not the same as the worldwide yard. The Swiss yard is bigger than the U.S. yard and stuff like that. So some of those apps are not written in the United States. So some of them, they're off because of that, because of the unit that's used in other countries is slightly different. So you do have to be careful with those apps. I'm not saying they don't work, because they do, but some of them, there are some that have errors in them because of that. Well, just for fun, sound like there's something cynical in there. What if we have 3 kilograms per cubic centimeter? Now I want to know, because we're capable of measuring pounds per cubic inch, but not kilograms per cubic centimeter. Over 1 cubic inch, right? Or cubic centimeter. Now, we have to get rid of kilograms and go to pounds. 1 kilogram is 2.2 pounds. Kilograms cancel out. We're left with pounds per cubic centimeter. We have to get rid of cubic centimeters. Go to cubic inches. Here's the problem. We don't have that conversion. We do know that 1 inch is 2.54 centimeters. How do I turn that into cubic inches? Well, what's 1 cubed? 1. Inches cubed is inches cubed. 2.54 cubed. Oops, helps if I get the cubed in there. Is 16.445, we're going to call it. We're going to round it there, centimeters cubed. Does everybody, any questions on where I got that 16.445? I didn't multiply it. I took it to the power of 3, right? Yeah, it's 2.54 times 2.54 times 2.54. You're correct there. It's just because we're cubing it, I have to cube the conversion factor. Remember, we said that's where the power on the unit affects the conversion factor, but not the other numbers in the problem. So 1 cubic inch is 16.445 cubic centimeters. So now across the top here, I've got 3 times 2.2 pounds is 6.6 pounds times 16.445. 108.537 or 108.54 pounds per cubic inch. That's pretty dense, by the way. I don't know of any material that's quite that dense. Other conversion factors we'll run into. Temperature. Our standard scale, US scale, is Fahrenheit. Does anybody know the metric scale? Celsius. And our benchmarks, we tend to talk about the temperature at which water boils and the temperature at which water freezes. In the Fahrenheit scale, what temperature does water freeze at? 32 degrees Fahrenheit. What temperature does it boil at? 212. Now, there's a little condition on that. That is the temperature that water freezes and boils at sea level at 1 atmospheric pressure, standard atmospheric pressure. Atmospheric pressure can vary. I mean, you might hear the weatherman talk about low pressure systems, high pressure systems. Atmospheric pressure can vary with those weather systems and with elevation. Like I have a friend of mine that lives in Colorado, and he's at about 6,200 feet above sea level, a little bit more than a mile above sea level. He said when he first moved out there, he had a hard time boiling eggs. Because he liked a 3.5-minute boiled egg because it was still just a little soft inside. Well, he said out there he'd boil that egg for like 4.5 or 5 minutes and it still wouldn't be cooked enough. Because water out there boils at like 198 degrees because of the lower pressure. So you had to, you can't get water hotter than that because it turns to steam and floats away. So he had to learn how to boil, boil it longer to get it to cook the same amount because you weren't getting the same temperature in it. So just a little qualification as to where those temperatures are measured at. In the Celsius scale, what temperature does water freeze at? 0 Celsius, and water boils at 100 degrees Celsius. Now there are two differences here. The one difference that we're used to is having the units be a different size. You know, the inch is bigger than a centimeter and whatever. Here, there's 100 degrees between freezing and thawing in the Celsius scale, and 180 degrees between freezing and thawing in the Fahrenheit scale. So 1 degree Fahrenheit is smaller than 1 degree Celsius. The issue here that we did not run into in our other measurements is right here. There's no common 0 point. In all of our other measurements, for lengths, 0 inches equaled 0 centimeters. For weight and mass, 0 pounds equaled 0 kilograms. Capacity, 0 liters equaled 0 gallons. 0 was nothing. It was 0. Temperature is the one measurement we have where there isn't that common 0 point. 0 Celsius and 0 Fahrenheit do not equal each other. So we cannot use a simple conversion factor. We have to use a conversion formula. So to go from Fahrenheit into Celsius, the Celsius temperature is equal to the Fahrenheit temperature minus 32, then multiplied by 5/9. That 5/9 comes from the ratio of 180 and 100. 100 over 180 will reduce to 5/9. Both of those divide by 20. So that's our formula. So that means, let's take human body temperature. 98.6 degrees Fahrenheit. To convert that, we put 98.6 in where F is. We have to subtract 32, which is 66.6. Multiply 5/9 times 66. Or you could do 5 times 66.6 divided by 9. That is 37 degrees Celsius. So human body temperature, 98.6, is 37 degrees Celsius. If I want to go the other direction, going from Celsius into Fahrenheit, I exactly reverse this process. Up here, I subtracted 32, then multiplied by 5/9. Down here, I'm going to start out by dividing by 5/9 or multiplying by 9/5, and then adding the 32. Notice there's no parentheses here. We're going to do the multiplying first and then add. Where up here we had to do the subtracting first and then multiply. So let's say you're driving into work and you happen to get a Canadian radio station. And they say the temperature today is going to be 20 degrees Celsius. Is that a cool day, a hot day, a nice day? Well, let's check. 9/5, we put 20 in where C is, plus 32. 9/5 times 20 is 36. 36 plus 32 is 68 degrees Fahrenheit. So a 20 degrees Celsius day is 68 degrees Fahrenheit. To me, that's a nice day. That's where I like it. But it's probably a little chilly for some. I'm going to have you guys try one in your notes. Use the correct conversion factor to convert negative 40 degrees Fahrenheit into degrees Celsius. I picked that because that's the coldest day I can possibly imagine. Or the coldest day I want to imagine. An answer yet?
Negative 40.
Yes, that is the one temperature that's the same on both scales. Negative 40 degrees Fahrenheit and negative 40 degrees Celsius are the same temperature. You would take negative 40 and minus 32, and then times 5/9, to 2 degrees Celsius. Negative 40 minus 32 is negative 72. 5/9 times negative 72 is negative 40. I know that one wasn't very nice.
I'm really doing something.
Okay, well, our next topic is to start talking about angles. And we've talked about angles a little bit already. We talked about angles being that difference in direction. You know, if we got a ray that goes off what we would define to be like an 18-degree direction, and we have another ray that goes off at what we would define to be a 71-degree direction, the angle formed between those two rays is 71 minus 18, or a 53-degree angle. We don't necessarily care how the angles are formed. We care what the angles are and what the relationship is between them. If I have an angle, two rays that go in exact opposite directions so that they form a straight line, that angle is 180 degrees. Very good. If I have two rays that form a square corner, that angle is 90 degrees. Right angle, right? And then, of course, we know a complete rotation is 360. Very good. And we can measure all of our other angles as fractions of those rotations. Well, often when we're measuring angles, we tend to use the 90 degrees, otherwise known as a right angle, as our benchmark. It's called a right angle because so many things you do, especially like building a house, when you have the floor set and you want to put a wall on it, the wall better form what angle with the floor? 90 degrees. That would be the right angle to put the wall at, as in correct angle. And the corner of the house better be 90 degrees. That would be the correct angle or right angle. And that's why it's called a right angle, because that is the correct angle to make most things. If we have an angle that is smaller than a right angle, that angle is called acute. Yes. The way you think about it is most acute things are small. So acute angle is smaller than a right angle. Ugly? No. An angle that's bigger than a right angle is called obtuse. My doctor says that I am classified as obese, so obtuse and obese sound similar as being too large, or larger than what's right. If you get into psychology, you might hear of an acute thinker and an obtuse thinker, or you might hear someone say you're being acute right now, or you're being obtuse. Acute means they can focus in, narrowly focus in, and just see all the details of a small portion of the picture, but they can't see the big picture. An obtuse thinker, they can see the wide angle, they can see the big picture, but they can't focus in on any little single spot and see the details. And we've already talked about what happens when we have these adjacent angles. If this angle here is 24 degrees, and this angle here is 31 degrees, what does that make this angle here? 55 degrees. I can just add them together. If this angle here is 23 degrees, and this angle up here is 67 degrees, what do they add up to? 90. What is that called? Complementary, yes. Two angles that create a right angle right up to 90 degrees are complementary. You can probably imagine what's coming next here. These two angles add up to 180, which is called supplementary. If I have two lines like this, that are exactly the same orientation, the exact same angle from zero for my direction, whatever, what are they called? There it is. Parallel. Now, many of us were taught that the definition of parallel lines are lines that never intersect or never cross. That's partially true. I mean, I can have lines that, let's say I have this line here and this line here. Do they ever intersect? No. But are they parallel?
No.
No, they're going totally different directions. In a flat plane, or in a plane like a flat piece of paper, just saying that they never intersect, that's adequate to define them as parallel. But in 3 dimensions, that would not be adequate because, like I said, those lines go totally different directions. They'll never intersect, but they're not parallel. The technical definition of parallel is always the same distance apart. The actual technical definition is everywhere equidistant, which means always the same distance apart. A line that cuts across other lines is called a transversal. It does intersect, you are right. And a transversal can cut across lines that are not parallel. That's just way more interesting when they are parallel. So, if this angle right here is 61 degrees, what's this angle right here going to be? You got it. 180 minus 61 or 119 degrees. How about this one over here? That one's 61. Remember those vertical angles we discussed a couple weeks ago. How about this one? 119 again. Now when I want to look down here, I can take this line here and realize that I can just slide it down and it sets right on top of that other one, doesn't it? So what that tells me is that this angle here must be 61, and this one must be 119, and yes, 61 and 119 again. Those 4 angles are the same as these 4 angles up here. Now there's a lot of fancy names for these. Like these 2 angles are called corresponding angles. These are called corresponding interior angles. These 2 are called corresponding exterior angles. These 2 would be alternate interior. These 2 would be alternate exterior. And there's rules like alternate exterior angles are equal, alternate interior angles are equal, corresponding angles are equal, corresponding interior angles are supplementary. We're going to cut through all the crap, and we're going to make up Hoff's rule. And my rule is, when you have parallel lines cut by a transversal, all the angles formed are either equal or supplementary. And for the most part, you should be able to tell. If they're two angles that are both acute, well, then they have to be equal. If they're both obtuse, then they have to be equal. You're like, this angle here and this angle couldn't be equal because one's obtuse and one's acute. The only time it ever really becomes tricky is if you have parallel lines like that and you have a transversal that's very close to being at a right angle. If it did hit at a right angle, by the way, it is called perpendicular. Now you might wonder, why do we need that extra term perpendicular? Why can't we just say it intersects at a right angle? Well, perpendicular is a little bit more powerful than just lines. Perpendicular means it's a right angle no matter what direction you measure it. For example, if you have a piece of paper, pretend that looks like a piece of paper, and you have a line coming out of that piece of paper, it's perpendicular if no matter what direction you measure it, that line is at a right angle to the paper. So it's right angle in every measurable direction is what perpendicular means. And then, of course, there's something called oblique lines. Forgot my U in there. Oblique lines might look like that. They're not parallel, they're not perpendicular. Oblique lines may intersect, they may not. But oblique is just, there's no special relationship. Not parallel, not perpendicular. So there's really no special rules covering them. Okay, that seems like a good place to take our break. Seems like I've talked for long enough for the first hour. Those of you at Ashland and New Richmond, you should have received your test back through email at about 8:50 this morning. I was in a rush to get them sent out, so the subject just says test in it. So it should be in your WITC email. Check. If it didn't come in, let me know. Those of you here in Rice Lake, I'll hand them back to you over break here. Let's take our break. It's 10:17, so let's come back at 10:27.